in section 10.1. We're going to talk about 3D coordinates. So what we're going to do is kind of step off the plane and into space. So what we're going to do is take our usual x and y coordinates, and we're going to add a z-axis. So that vertical axis is z. Normally we do the y that way, and the x kind of coming out of the page there. And then a point in space has 3 coordinates. Instead of an ordered pair, we get an ordered triple. So we have an x, a y, and a z. And the way we can visualize this, if we project this down onto the xy plane, there's where it hits the xy plane, and this is projected over here. That would be my y coordinate. I project this over here, just like we do in the xy plane. That would be the x coordinate, and then I project over here, and that would be my z coordinate. So that's a point in space. We call this we're going to work with what we call a right-handed coordinate system. And that means if the z-axis goes through our heads, our right hand points along the x-axis and our left hand points along the y-axis. If our left hand was pointing along the x-axis, then we'd have a left-handed coordinate system. But we normally work with a right-handed coordinate system. So we always draw our x and our y this way. The coordinate axes, we have now instead of just an x and a y, we have an x and a y and a z. This also divides space into, we could extend this so we get the negative y-axis there, the negative x-axis there, and the negative z-axis there. Divide space into 8 octants. So we have 8 octants. Instead of 4 quadrants, we have 8 octants. The first octant is where x, y, and z are all positive. So out here above the xy plane. And then our octants go counterclockwise, just like our quadrants. So the second octant would be back here, the third octant back here, fourth octant here. And then we start below the xy plane, under the first octant, and we get octant 5, 6, 7 back here, and 8 below over here. Normally usually we work with the first octant, where x, y, and z are all positive, but our octants go counterclockwise around the z-axis, 1 through 4 on top, and 5 through 8 below the xy plane. And in addition to coordinate axes, we end up with coordinate planes. So we have the xy plane, which is our familiar plane. And on the xy plane, z equals 0. So that takes us down here onto this flat xy plane. We also have the yz plane. That's this vertical plane here. This is kind of standing upright there. On the yz plane, x equals 0. And then we have the xz plane also. That's the plane here that's made by the x-axis and the z-axis. On the xz plane, y equals 0. So we'll talk about the coordinate planes in 3 dimensions rather than just the coordinate axes. So we have a right-handed coordinate system. We have points defined by an ordered triple rather than an ordered pair. We have our 8 octants and our 3 coordinate planes. All right, questions there? Okay, let's plot some points. Just a little bit of practice plotting points in 3D. So 3, 2, 3. So here are my axes. There's Z, Y, and X. So I'm just going to plot these in the XY plane. So here is, I'll do this in red, here's X equals 3. So I'm going to go over here. Here's Y equals 2. So there's the point 3, 2 in the XY plane. And then I'm going to go up 3 units. And there's Z equals 3. So there would be my point. 3, 2, 3. Yes?
Why is the being visualized in the foreground instead of in the second object? Is it just a visualization thing, or is there like a mathematical reason for that?
It's just the way we usually draw it, with the first octant being like the closest to us.
Okay.
Just like it's normal, our standard way of doing the XY plane is to do it like that.
Would it actually matter if you rotated 90 degrees?
No.
Okay.
It's just usually will work in the first octant, so it's easier if that's the closest one to us.
Okay.
All right, let's plot. Questions on how we plotted that point? Yeah.
So it's not like units from the XY, it's like 0.30 or 0.3 on Z, I guess. Like
It's 3 units up from the XY plane.
okay.
So if this were if the XY plane were a flat surface, we would go 3 units up to get to here. And if I go straight across to the Z-axis, that's going to be 3 units up. So 3 units up from
It's
here.
not like 3 units from the other.
Yeah.
Oh, it is.
So the point would be 3 units up. So if I counted up from here, that would be 3 units. All right. So let's plot another one. Let's plot. -2, -1, -3. So there are our axes. So I'll do this one in blue. So X is -2, so I'm going to go 2 units back this way. There's -2. Y is -1, so I'm going to go 1 unit back this way. So there's -1, so I'm going to project those back like so. There's my points in the XY plane, -2, -1. And then I'm going to go down 3 units. And that would be the point -2, -1, -3. And that would be -3 there. 3 units below the XY plane. Kind of going back and down. All right, questions there? Do we need to see another example? Good. We won't have to plot a lot of points in 3 dimensions, but part of what we want to do today is just get a little bit more comfortable visualizing things in 3 dimensions. Okay. We have a couple of familiar formulas that we'll use in 3 dimensions. The distance formula and the midpoint formula. So we have 2 points, x1, y1, z1, and x2, y2, z2. Our distance between those points. It looks just like our distance formula in the plane. We just add another piece for the z part. Square root x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So we're just adding the extra piece for the z coordinate. And basically we're doing the Pythagorean theorem twice to get this. So this first part looks just like our distance formula in the plane. Just add the z part. And our midpoint between these 2 points. Just like our midpoint formula in the plane, the average of the coordinates, x1 plus x2 divided by 2, y1 plus y2 divided by 2, and z1 plus z2 divided by 2. So we're just averaging each coordinate to get our midpoint. And I'm not going to do a lot of calculations with these. We should be able to calculate these. So we're just adding a z piece. All right, we have one nice surface, a 3-dimensional shape that we can come up with a nice formula for. Anybody have a guess what our friendliest surface in space is going to be? Sphere. Sphere is our nicest, friendliest shape. So the equation of a sphere. Turns out that the equations of lines in 3 dimensions are a little more complicated than they are in the plane. Equation of a sphere. What's a way that we can visualize, how can we think of a sphere related to something that we know in 2 dimensions? So like a circle, like a 3-dimensional circle. Our formula is like a 3-dimensional circle. So we have a center, h, k, just like in the plane, and then we're going to add an a, j, h, k, j. That's our center, and our radius r. Our equation is x minus h squared plus y minus k squared plus z minus j squared equals r squared. So we're just adding, just like the other equations, we just add a piece for the z component. So nice, easy, something that we're used to working with. And the points that we're talking about on the sphere are just on the surface of the sphere. It's not the part inside, it's just the surface. So let's look at an example using this. X squared, we want the center and radius of the sphere, and our sphere is given by x squared plus y squared plus z squared minus 2x plus 6y minus 4z minus 2 equals 0. So what are we going to have to do here? What do we do? Complete the square. How many times? 3 times. One's for the x, one's for the y, and one's for the z. And we can tell this is a sphere, just like we did with our conic sections. All the coefficients in front of the x squared, y squared, and z squared are the same, and they're all positive. So this would have to be a sphere. We can get all kinds of other types of surfaces. In Calc 3, we talk about paraboloids and ellipsoids and hyperboloids, and the rules are very similar to what we just talked about with our conic sections in terms of our coefficients. So let's find our equation here. So I'm going to group the x's and the y's and the z's. X squared minus 2x plus y squared plus 6y plus z squared minus 4z equals 2. No leading coefficients, so this is nice, easy to complete the square here. So when I complete the square here, I get x squared minus 2x. What do I add here? Plus 1. And I'm going to put this over here. 2, I need to add a 1 there. Plus y squared plus 6y. What do I add to this one? Plus 9. I'm going to add a 9 here. And plus a z squared minus 4z plus 4. Plus 4. Keep everything balanced, so I get an x minus 1 squared plus y plus 3 squared plus z minus 2 squared equals 9, 13, 14, 16. So our center is 1, negative 3, 2. And the radius equals 4. So familiar process. We just add a piece for the z, just like with the other things. All right, questions there? Okay, the last thing we need to talk about today, another tool that we'll use for surfaces in space is called the trace. Trace of a surface is something that we'll use. Trace of a surface, all it means is the equation or the shape that happens when the surface intersects a plane. And really, the only surface that we're going to talk about in this little bit that we do in chapter 10 is a sphere. So what could be the trace of a sphere when a plane intersects a sphere? A circle, or what else could happen with a sphere? A point. It could just be sitting right tangent to a plane, or it could have no trace if it doesn't intersect. If we're talking about one of the coordinate planes, if it doesn't intersect the coordinate plane at all, we say it has no trace in that plane. Normally, we'll look at the coordinate planes. We'll look for the trace of a surface in a coordinate plane, in the xy plane, the yz plane, or the xz plane, and that helps us visualize what the shape's going to look like. So let's look at an example. Traces are really easy. We want to describe which trace do I want? The xz trace of the sphere x minus 4 squared plus y plus 3 squared plus z minus 1 squared equals 25. So we want a description. What happens when this sphere intersects I said XZ, the XZ plane. That's what the XZ trace means. So what do we know? What's true in the XZ plane? XZ plane, y equals 0. So what this is asking us to do is substitute y equals 0 and simplify. So I substitute y equals 0 and I get x minus 4 squared plus 0 plus 3 squared, 9, plus z minus 1 squared equals 25. Subtract 9, so I get x minus 4 squared plus z minus 1 squared equals 16. So the xz trace of this sphere would be a circle with a center at x equals 4 and z equals 1 with radius 4. So that would be the trace of that circle in that plane.
Are we going to have to worry about planes that aren't along x, y, or z?
No.
Okay.
And when you go further with these, with different kinds of surfaces, you talk about paraboloids and ellipsoids. So the trace of a paraboloid in the coordinate plane is a parabola. So a paraboloid looks something like this. You have a parabola, and then so that would be a parabola. This solid, this surface. So that's like the mirror of the flashlight that I was talking about when we talked about parabolas. Would be a paraboloid. An ellipsoid would be like kind of a football shape. That's an ellipsoid. And the trace of an ellipsoid in the coordinate plane could be an ellipse, or if depending on which way it's intersecting, it could be a circle. Hyperboloid, you have hyperbolas. That would be your traces in your plane. So it just gives us a way to visualize surfaces. What would be the possible trace of a cone? Circle. So if you look at it from the top, it's a circle. What about aren't the sides of the cone straight? So the trace of a cone in a plane, one of the coordinate planes, could be two lines. So rather than a curved side, you have straight sides, and then there's your circle for the top of your cone. So it just gives us a way. Traces give us a way to visualize surfaces. All right, questions? Okay. Every other even, every other odd there.